In this video, we're going to work some related rates problems. In the video where we go through the related rates section of the textbook, we talk about how there's a couple of different ways you can approach a problem like this. But for the problems in this video, we're just going to use the method the textbook shows, the method that I like to use for these types of problems. A baseball diamond is a square with sides 90 feet. A batter hits the ball and runs towards first base with a speed of 24 feet per second. A, at what rate is his distance from second base decreasing when he is halfway to first base? And then B, at what rate is his distance from third base increasing at the same moment? Okay, so remember the nature of a related rates problem. You've got some rate that you know. You have a system that you're dealing with, and you have a rate that you know. But you want to find another rate, but you can relate that other rate to the rate that you know. You relate these variables with a formula that doesn't involve the rate of change of those variables, but once you have that formula, you differentiate the formula with respect to time or the variable you're interested in, or the independent variable you're interested in, and so you can solve for the rates. So for part A, we're looking for the rate that the distance of the player from second base. How is that changing? So if we draw the baseball diamond, so in general, we're going to draw the most general case. Let's say the player is here, just somewhere along the first baseline. Okay, so we have his distance from first, his distance from second, and then we will also put third as well. Okay, we'll call this X. That's this distance. We're going to want to relate these distances, the distance from second and third, to X, because we know the rate of change of X. Okay, what else do we know? We know that this is 90, this is 90, and this is 90. We'll call this S for second and this T for third. Okay, so again, the idea is there's a rate that we know, and we're trying to solve for another rate that we can relate to the rate that we know. But our root equation that we're going to use to solve this is just relating the variables, not the rate of change of the variables, just the variables themselves. So how can we relate X to S and to T? Not at the same time. We can have two separate equations that one relates X to S and another equation that relates X to T. Let's start with S. Well, this is a square, right? This is a right triangle here. So we can use the Pythagorean theorem. X squared plus 90 squared is equal to S squared. Okay, 90 squared is 8,100. So okay, so there's our equation that relates X to S, but we're looking for the rate of change of S. That's what that's what we want to know. The rate of change of the distance of the batter, the player from second base, that straight line distance as he runs up the first base line. So we're looking for ds dt. So let's take the derivative of this equation with respect to t. Okay, so we just need to use the chain rule. What is the derivative with respect to t of x squared? Chain rule, because x is a function of t. So what is the derivative of something squared? It's 2 times that something times the derivative of that something. That's just dx dt. We're going to put x dot. Plus d dt of a constant is 0. Okay, d dt of s squared to s dot. So now we just need to solve for s dot. So we could divide both sides by 2. Okay, so s dot is equal to That's interesting. The rate of change of s with respect to time is a function of this distance times the distance that the rate of change of this distance and this distance. Interesting. Okay, so we have x dot, that's 24 feet per second, but we need x and s. Okay, well, we know x because it says he's halfway to first base, so x is going to be 45. What does that mean s is? Well, 90 squared plus 45 squared, 100.6. Okay, so we've got x, s, and x dot, but this is the tricky part about these problems, in my opinion. What do we plug in? Like, is x dot positive or negative? Is x positive or negative? Is s positive or negative? The way you look at this is you come to your formula that you use to relate the variables, and you look at that like from as literal of a standpoint as you can. Like, what is this formula? In this case, this is geometry. This is all about a triangle. It's about this right triangle. That's what this formula is about. So, x dot is, what is that doing to the side length of this triangle? It's decreasing the side length. So x dot's going to be negative. We're going to put negative 24. Okay? Now, for the side lengths, x and s, well, those, for a geometry type problem like this, those are always going to be positive because you can't have a negative side length. Okay? So s dot, we'll put 45 minus 24, okay, and 100.6. Minus 10.7. This is negative. Does that make sense? Yeah, this length is getting shorter. It's approaching, it's going from, it's approaching 90. Okay, at what rate is his distance from third base increasing at the same moment? So, okay, same process. We have, so if we call this, let's call this y. So, y squared plus 90 squared is equal to t squared. So d, so we've got 2y, y dot is equal to 2t, t dot. So t dot is equal to, okay, we're going to have y is going to be 45. And t is going to be 100.6. But y dot in this case, the 24 feet per second, is going to be positive because this length is increasing. So we get the same answer. But this is positive, right? Because the length of t is increasing. A boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, so what rate do we know? We know the rate of change of this length here is 1 meter per second. Okay, and what we're looking for is the rate of change of the straight line distance of the boat from the dock, right? How fast is the boat approaching the dock? So how can we relate this distance to this straight line distance? Well, that's a right triangle. So okay, so we'll call this x, and this is a fixed distance. That will be, the pulley on the dock is 1 meter higher than the bow of the boat. That's 1. Okay, and then we'll just call this y. The length of the rope. Okay, so we can relate x and y with the Pythagorean theorem. X squared plus 1 is equal to y squared. Okay, now we just need to differentiate this because with respect to time, because these are both related to time. X and y are both related to time. They're related to this independent, they're both related to the same independent variable. Okay, d dt. So the derivative with respect to time of x squared, x is a function of t. This is the chain rule. 2x, x dot. Go to the chain rule section in example problems to learn about the chain rule, and then we differentiate equations like this in the implicit differentiation section. Okay, d dt of 1 is 0, and then 2y, y dot. So now we just want to solve for the variable that we're looking for. What are we looking for? We're looking for x dot, the rate of change of the distance of the boat from the dock. There we go. Okay, so now this is the challenging part, in my opinion, for these problems. What do we put for y dot? Like well, not what do we put, but do we put positive or negative? Do we put positive or negative for y, positive or negative for x? Well, okay, again, you come back to the formula you use to relate the variables. We use the Pythagorean theorem. That's all about a triangle. So look at the triangle. Look at the literal meaning of the equation you use to relate the variables. Y dot. What's happening to this length? This length of this triangle. Well, okay, it's being pulled in at 1 meter per second. It's decreasing. Y dot's going to be negative. Y dot's going to be negative 1 meter per second. Now, we also need to put x and y at some moment. It's going to be the moment whenever the boat is 8 meters from the dock. So x is going to be 8, but positive or negative 8. Well, for this, the side lengths will never be negative. You can't have a negative side length of a triangle. So this is just going to be 8. And then y, just use the Pythagorean theorem. 8 squared plus 1 squared is equal to y squared. So, well, that's just the square root of 65. Okay, so let's just plug this in. So we've got root 65, negative 1, 8. So negative minus 1.01. Does this make sense? Yeah, x, this is getting, it's the distance between the boat and the dock is decreasing. So this is the answer. A swimming pool is 20 feet wide, 40 feet long, 3 feet deep at the shallow end, and 9 feet deep at its deepest point. So it gives us all these dimensions here. A cross-section is shown in the figure. If the pool is being filled at a rate of 0.8 cubic feet per minute, how fast is the water level rising when the depth at the deepest point is 5 feet? So we're looking for the water. This is the water level. which is also the depth at the deepest point. That's the water level H. And so with these related rates problems, you have a rate that you know. And you want to use that rate that you know to find another rate. You can find that other rate with an equation that relates those two variables. The variable that you know and the variable that you don't know. So what we need to do is get an equation for what do we know? We know that the pool is being filled at we know the rate of change of the volume. So we need a formula that relates the volume to H. So what we can do is we can break this up into areas. So there's the water level. We've got a triangle there, a rectangle there, and another triangle. So the area of like this triangle times the distance into and out of the page of the pool, that's the volume of that region. Add those volumes up. So, okay, what's the depth into and out of the page? It says the swimming pool is 20 feet wide, 40 feet long, and 3 feet deep. At the shallow end, 9 feet deep at its deepest point. So 20 by 40. This is 12 plus 16 is 18. Plus 16 is 34. Plus 6 is 40. So it's 20 feet into and out of the page. So with that, let's write a formula for the volume. So with the rectangle, we've got 12 times H. 12H times 20. Okay. Now, the triangle, the area of a triangle is base times height divided by 2. The base here is not 6, right? It's shorter than 6. But we can use similar triangles. So if we've got this larger triangle here, so we know this larger triangle is 6 by 6, right? See how this extends? It's 6 by 6. So we can say that if we say this unknown side is x, 6 divided by x is equal to 6 divided by h. So 6x is equal to 6h. X is equal to h. Okay, so base times height, which is h times h divided by 2. So h squared divided by 2 times 20. All right. Now, okay, we've got base h times, or no, that's the height. Height times base, same deal here. So we need to use similar triangles again. We know that this height is 6, this base is 16. So, okay, 6 divided by h is equal to 16 divided by, we'll call that x again. This is this unknown length x that we need. We need the base of this water, of this triangle that's created by the water. So now let's solve for x. 6x is equal to 16h. X is equal to, so 8/3 h. Okay, so the area of this triangle is base, which is the x, so 8/3 h times height divided by 2 times 20. Okay, so now let's just simplify. So 12 times 20, 240. Okay, and then this plus 10h squared plus, so 80 over 3h squared. 240h, and this is 30 over 3, so 110 over 3h squared, right? We just added these fractions. Okay, there we go. That's our formula relating the volume to the height. Now we want to differentiate this equation with respect to time. So V dot is equal to 240h dot plus, so what is 2 times 110? That's 220 over 3, okay, now h and then h dot. Now let's solve for h dot. Okay, so 240 plus okay, now we can simplify this. Let's multiply this by 3 over 3. So we've got, what is 240 times 3? 720 plus okay. Now we just need to plug in. We're trying to solve for h dot. We just need to plug in v dot and h. What are the signs of v dot and h? Well, let's come back to our formula here. This formula. There's having h be negative makes no sense here. There's no such thing as a negative h when it comes to what this formula represents. So h is going to be that it tells us what is h dot when h is 5 feet. Okay, so what about v dot? Well, v dot could be negative. You could be like pumping water out, but it tells us that the pool is being filled. So this is going to be 0.8, positive 0.8. It tells us that v dot is, that we know that v dot is increasing. So, okay, 3. Okay, so h dot is equal to 3 times 0.8 divided by so this is going to be in h dot. We kept our units, consistent. So this is going to be in feet per minute. So that is, so 1, 2, 3, yeah. 1.32 times 10 to the minus 3. And that's going to be in feet per minute. And what we could do is, if I was reporting this to somebody, we could change this. Like, this is the answer. Okay, I guess, like, the textbook's going to give you this answer, but we could change this to feet per hour. So 60 minutes in 1 hour, so we can multiply this times 60. And that's still 0.079 feet per hour. Let's multiply that times 24. There we go. This is the same thing as 1.9 feet per day. That I can conceptualize that a lot better than if someone told me 0.00132 feet per minute. I mean, like, I can't even think about what that means. Okay, so this is also, I guess, in the back of the book they won't put this, but you can consider this a correct answer as well.